Over. Can you guys hear me okay? Somebody give me a hand sign or something.
We can hear you.
Awesome. Thank you so much. Cool. All right. Well, we're going to jump in, and I think we'll get a couple more people coming, and we'll add them as they come. Today, we're going to just kind of wrap up our section on inheritance. We're going to look at kind of a really cool application. You'd be surprised at how common it is when you try to design things kind of smartly, where you can reuse some code. But it is a little tricky, and so we're going to go over it step by step. Most of what we're going to do today is going to be aiming toward kind of one of our final homeworks where we can kind of overload things in a really smart and optimal way. And so everything that we do today in our practices is going to progress toward that solution. So we'll get into that. We'll have probably about 4 or 5 different exercises that we'll go through for that. But let's start off just looking at the schedule again. So we're right here, basically week 14. So as I know, everybody was working hard on quiz 5 and homework 7, and mostly got all that in. I know some folks are still working on stuff. I'll definitely be here at lab tonight to answer any questions you have on that. We'll go over briefly homework 8. I know it's kind of piling on right after you guys just finished 7. Hopefully it'll seem pretty easy. It's really probably a 1-week assignment, but I'm giving you 2 weeks for that. And there are 2 options we'll talk about in a second. If you're bored with kind of what you're currently doing, this will give you a chance to either do more of the same or something different. And then we're going to talk about inheritance today. And if we get through all that, we'll talk about threads on Thursday, which is a really fun advanced topic, quite different. And I'm anxious to just give you guys some exposure to it so that you can go out into the world and maybe, pick it up in some other language. It's a very common concept and one that hopefully you'll get a chance to play around with sometime in your careers. So kind of the way it lays out today, we'll do a couple slides on homework 8. I will come back to this, every lecture we have to just give off little hints as we go through the lectures. So, you're not starting too much from scratch. We'll review inheritance real quick from last lecture so you remember some of those concepts. And I'm going to go over the lab. I haven't done these before. I just put it out there. I'm going to see if it, helps you guys. I'll just briefly go over the solution for this. It's stuff that, you should have been able to understand the stuff from the last lecture, but just in case, I'll go over it again. And then we're going to talk about virtual functions and dynamic binding. So this is the key principle that we need to take advantage of in C++ to really do some very, very cool overloading of methods. And so one of the examples we've used is you've got a sort of a base class creature, and then you derive multiple other creatures, and they have their own methods for moving around. And so virtual functions and dynamic binding allow us to attach intelligently to the move function in the child or the descendant, original descendant that might have its own move function. So it gives us these very, very effective fallbacks in case every descendant doesn't have its own move function. And we'll talk about why that's cool and how we actually go about setting that up. And then we'll talk about some nomenclature. This is just the way people talk about classes in C++. Abstract and interface classes will help you understand what those are and how they actually come to pass. There's not a keyword abstract or interface. And so sometimes these things are a little mysterious, but once we introduce the rules to you, you'll be masters of this. It'll be really easy to do that stuff. And then we'll just kind of close things out by exposing and hiding base members from the base. There's a way actually to override some of the protections that the base class might put in. So we'll look at how we can actually do that. And then our last topic for today will be multiple inheritance. Multiple inheritance means kind of like you've got 2 parents you're inheriting from, and so you want to find, and those are represented by 2 classes. So how would we go about doing that if we were doing a descendant based on 2 parents? And why would you want to do that? So we'll look at that. So any questions on our layout for today? Very good. Okay, cool. Well, let's dive in then, because it's kind of a big lecture, but I don't think it's too complicated. So homework 1 is homework 8 has 2 options. So I wanted to give people a chance to kind of keep forging ahead with the same problem that we've been working on in 7. and just convert that over to shared pointers. So obviously you got to get wrapped up with homework 7, and I'll be here to help whoever needs it on homework 7, make sure you feel good about that. But then homework 8 is just, hey, let's convert those raw pointers over to shared pointers, given all that we learned about shared pointers. So we'll go through what that means, but that's kind of option 1. And the idea is you don't want to have a puzzle of pointers to tokens. We want to have shared pointers to tokens. And we want our grid to also use those shared pointers, right? And we need shared pointers, not unique pointers, because unique pointers wouldn't allow us to point to the same token by 2 different pointers. So we're going to definitely be needing shared pointers in this case. And then the big key thing is eliminating all references to the keywords new and delete. And why is that? Because if we're using shared pointers, we don't have to worry about cleaning up the garbage. We don't have to, in our destructors, delete the instances of the things that we created on the heap, because the shared pointer will do that for us. So that code that you presumably wrote in your destructors for homework 7, you can just throw it away in homework 8, because we'll be using these shared pointers, which is great. And then just to stretch ourselves, we're having a requirement that you use make shared everywhere. So the word new will not happen anywhere inside of your homework for homework 8. And then you can just submit the files that you may have changed, or your Replit link if you're using Replit, just like before. Okay. So visually, here's kind of how that lays out, right? So if we were going to do a vector of shared pointers of tokens, it's our pieces vector, which that should be fresh in your mind. And then inside of here, we just tell it we're going to collect some shared pointers in the vector, right? So we're just letting it know the types of things that we're going to collect, right? And then when we read our files, we'll go ahead and instantiate those tokens like we did before, but we'll do it using the make shared, right? So we're going to be actually invoking make shared in order to call the constructor, or have make shared call the constructor to create each token, right? Now that is different than what we had over here for our grid before. Our grid, we had a vector of token pointers, right? So now we're going to have a vector of shared token pointers. Okay? And the way we assign those to the grid will be pretty much identical to how we assign the pointers in your homework 7, but you'll have a chance to kind of work your way through that. So at the end of the day, we get the benefit of shared pointers that clean themselves up here, and you have a relatively small amount of code to change. It's a little confusing, but it's not a huge amount of work. So if you do it while, before this shared pointer knowledge seeps out of your brains, it'll be a little easier. So that's why I wanted to give it to you here. So here's the hookup stuff that we saw before, right? So we literally just say grid 0, 0 equal pieces of 0, 0. And as you may recall, this would call the assignment operator to assign the shared pointer across from the pieces array over to the grid array. And all that just works magically. So it looks as if we're just, doing what we did before with raw pointers, right? So that's going to be, that's the option 1 on homework 8, right? And so just kind of summarizing there, we don't need to do the delete as we talked about, and the rest of all that I think should be pretty much flow from what I described, right? So if you find yourself using new, stop right there and step back and review make shared. There should be no new used in your homework 8 if you choose this option 1. Okay, I think that's our last slide on our way. Yeah, any questions on homework 8 for option 1 there? Okay, cool. All right, well, good. So yeah, hopefully some of you guys will take that path. It's quick, it's easy, kind of not quite a gimme, but I didn't want to burden you too much. Now, if you're looking to stretch a little bit, we talked a little bit about this idea of Facebook and how would you hook these things up. So I put this one out there just in case you felt, okay, I got homework 7 down. I understand all that. I'd really just like to go do something new. So this is a different approach. So the idea here is we're going to implement a Facebook class. It's going to load a data file of names and these one directional friend lists. And this, takes you through a number of common problems that it's good for you to have to deal with. first off, we'll have to create a person class, or instance rather, for each person we load from the file. And we're going to use shared pointers for that inside of a people map, right? So we'll have a super fast lookup. If we got the person's first name, we should be able to get access to their shared pointer very easily. So it's not too different than what we're doing inside of the puzzle. But this time we have a name, we can look stuff up. And we have that key value pair map to let us do that. So the name is the key, and the value of the map is going to be the shared pointer. Okay, and that's going to point to our person instance of a person class. So we'll use a vector to hold all the shared pointers to each person's list of designated friends. And we'll look at a picture of this in a second. I know the text is kind of hard to absorb. And then what we want you to do is link up all these things, right? And you'll see as we go through this data file, the tricky part of these kinds of loaders is that the friends don't exist yet, right? So as you're loading up one person in their friends list, the friends don't quite exist yet. So you can't really hook up the pointers on the first pass through the data, right? So, and here again, you know, we won't be using any new or delete. We'll just be using the make shared. So, and then at the end, the idea is just print out all the stats about who has how many friends, just to test out that all your pointers are working well. So here's how the data file looks. This will kind of bring this into focus a little bit. So each line indicates one person and their friends, right? So take Tia. Tia has 4 friends on her list, and her friends are Jean, Lillian, Allie, and Jacob, okay? So the first one is the person's name. The second item we want to read is the integer friend count. And then depending on that number, we'll end up having to read a certain number of friend names. So this might challenge your memory a little bit on how you're going to loop through and parse these files. You know, you've done this before in various shapes and forms, but this is maybe a little bit different. But you should be able to load this stuff up. The trick is that when you load up Tia, Jean, Lillian, Allie, and Jacob may not exist yet. So many of you are going to try to assign a pointer to Jean right off the bat as you're reading in Tia's friends, but Jean hasn't been loaded yet. So you're gonna have to think about how you're gonna go about doing that. One strategy is to read the file twice, totally fine in this case. And if you read the canvas, it will take you through some steps for that. But there are other ways to do it too. So you could cache that string and then come back later and then maybe you know, reinstantiate or relink up stuff after you've loaded everybody in. But definitely if you try to just use the map right off the bat, it's going to fail, and it's understandable. Some folks will do that before they remember this conversation. The other key thing about this is to remember that the friend lists are one directional. So here's just an example. Chantel has 0 friends and Keaton has 5. And one of Keaton's declared friends is, of course, Chantel, but Chantel, it's not mutual. So Chantel is referenced by somebody, but Chantel is not necessarily referencing that same person, okay? So, so this is a potential issue if we were using pointers to try to track how many people were pointing to Chantel. Like we talked a little bit about the cyclic pointer, self-referencing pointer problem last week. And so this would potentially raise that issue if we were to try to keep track of those kind of references. So here's kind of how that would look then. So we have this people map, right? And the first pass we can do is we can kind of create instances for everybody. And we have our empty friends vector of shared pointers to other persons, right? To other person records, right? And there's our Tia key value pair, right? The key is Tia and the value is the shared pointer itself, right? Points to a person instance, right? And we build all those things. And then the second pass, we'd actually read the file again, or if we cache those strings somewhere, we could do that that way. But we go through and we hook up all those pointers, right? There's a very common pattern. A lot of times when we serialize or store some complicated network of pointers out to a file, we write all those things out, but when we read them in, the order in which we read them in can pose some problems. And so this exercise will take you through that. Now there's an optional non-bonus kind of thing there for those of you who want to implement the weak pointer, so you can keep track, so Tia can know how many people are referring to her, even though they may not be in her friends list. So that is described in the Canvas, and for those of you who want to give that a try and try to implement that thing we talked about, that's there. But it's not a requirement, and there's not bonus points on this particular one, but you may find it interesting to pursue that one. So any questions on part 2, homework 8? Okay, all right. Well, we'll come back to it again. I know it's kind of throwing a lot at you, especially coming off of homework 7, but it's really not too bad of an assignment, especially if you take the first option 1, but both are totally valid. So let's just quickly review inheritance part 1 to just familiarize you again with the syntax. So first off, we talked a little bit about some new classifiers in our base, or our grandparent, if you will, but the base class here, foo, can declare not only public, but it can declare something to be protected, which is somewhere between private and public. Protected means we're keeping it in the family. That means that foo junior can actually make use of X, and that's totally fine, but we couldn't actually access it publicly, right? So, so we can do foo junior FJR, but we can't do JFR.X from outside, or, think of it as main, or, but, through an instance of the class, we cannot have access to X. That would be as if X was public. Okay, so we learned a little bit about protected, right? And we won't go into all the permutations of these things because I know they can kind of wind you up in knots, but that's the main one that gets used, right? So here's another example. So we create a creature, right? So we call this base class, and it has a protected weight, right? So and then we have goblin, right, which derives publicly from creature, right, which is the very common way we would do that. So remember, these are 2 different publics. This one up here tells you how you're inheriting and how you're going to pass that inheritance on to your descendants, and this one just talks about how you're classifying your data members and your methods, right? So try not to get those confused, right? So we said we can, if we want, access this protected weight member in the implementation portion of the goblin's constructor. That's okay. So that if somebody wants to create a goblin of a certain weight, they could pass in the value in the constructor, and we can assign it that way. But we said that we still have to have default construction for our base class. And the reason is because it's always going to get called unless we call it explicitly. So we can do that. It's just not the most ideal way to do it. We'll see and review the better way. Okay. So so here's calling the constructor from the constructor list, right? So here's the same thing, but this time what we're doing is we're telling the creature constructor what we want to feed it. So we're saying, hey, call creature constructor with the GW, and then I'll go and do whatever I need to do for the goblin down here. Okay, so that's really the better way to do it. And that way we don't have any implementation there. And it's really actually the most optimal way to do it because we're only calling the constructor one time for the base class, okay? And we're not overriding GW or the weight again, okay? So that was really the better way to do that. That's how we should go about doing that anytime we're actually initializing classes. And now it's true, if you don't have a default constructor here for your creature and you do call it this way, then you'll be okay. But anytime you call it and forget to put this into the initialization list, you're going to end up with compiler problems. So it's always a good idea to have your classes have these default values anytime, or default construction anytime, especially in situations where you're inheriting, okay? So, and we said, just so we don't forget, we cannot invoke try to initialize the base class as members through the initialization list on Goblin. That's a no-no, that won't work, right? We just can only really call the creature's constructor directly, okay? So that's a bad situation. And then we talked about overriding methods, and this is really what we're gonna do a lot of today, right? So we said the base class could have a move a move member in it, move function, right? That might move in a certain way. And if the goblin implements one, then the goblin's move is going to shadow the base class's move. And depending on a few factors we'll talk about, one or the other of these move methods will get called. And so there's lots of ways to control that. We looked at a few of the ways to do that with scoping statements that allow us to specify that very explicitly. So both of them exist. They actually are both there in every instance of a goblin has both of these move methods. So it really just depends on how we go about invoking it. So we could say creature.move, and that would call the creature move, and goblin.move, if called off an instance of a goblin, will actually call the goblin's move method, okay? And we'll see how to actually turn that into something a lot more useful. Any questions on that review part before we kind of dive into the new material? Okay, cool. All right then, let's forge ahead, and I'll try not to lose anybody. Actually, and before we kind of dig into the new material, let me just go over this real quick. So this was a little bit lengthy, but we said, hey, just what would it be like if we wanted to create a chain of inheritance? So probably you got the concepts right, and you think, oh, that's pretty straightforward. But you know, when you sit down and do it, you kind of run into little gotchas. So I'll just kind of skip over this because I think you guys saw this. The idea was just to give each person in the chain, the hierarchy of classes, one data member, and then have those cascade down and then print things out. And then we also said, put some messages in the constructor and the destructor so you can actually see what happens when these things unwind, when they construct and when they destruct automatically. So here's kind of the look at that again, and then we'll look at the code. So basically, if we were to instance a grandchild GC, just the grandchild, right? First thing is going to happen is the constructor for the grandparent should get called, and we could print out the value that it sets either by default or whatever we pass it if we call the grandparent constructor. And then the parent does that, and then the child does the constructor, and then finally the grandchild does its constructor. And so once the main is over or GC goes out of scope, then we start unwinding from the child toward the base class, right? So the order is construction goes from the grandparent to the child, and destruction goes from the child to the grandparent, right? So important to remember that order because sometimes you can get caught up in weird bugs. And if you remember that, it might explain a few things to you. Because you can imagine if your destructor for the child decided to delete something that the grandparent was reliant upon, then you could run into some problems there. Okay, so here's the code. There's our main, right, and there's our grandparent. Notice that we have our default construction here, right, and we can initialize its own member A based on what's passed in, and remember what's passed in might come from the parent class that's calling us through that chain, that hierarchy chain, right? So, so here is, and in this case, we just use the default constructor for the grandparent, but we derive publicly from grandparent. We add a member B, and then we initialize our own B, and we allow the default construction of the grandparent to set the value of A. So now we can print out A and B, right? Right? And remember, again, that's different than that public over there, right? Those are two different publics. Here's the child. See, they look very similar, right? Just one member per. And again, all these things are getting default constructed in sequence. Now, when you sit down and you look at a blank piece of paper, you think, oh, okay, well, maybe I should design the grandchild and work my way backwards. And you start thinking, okay, what do I got to initialize? But if you use the default constructor here, it's quite simple, right? We're just initializing our own member, and we're letting the default constructor of the predecessor deal with its own stuff, and it just works its way back up the chain. And there's the grandchild and the printout, and that's how we get basically that printout that we saw before. So that's a good exercise to work through if you haven't, or if you find yourself needing to refresh it. This is a good one to just try and see if you can do it. Any questions on that? All right, very good. Okay, so for today's stuff, now this sounds kind of scary and bizarre, but it is really one of the cool things about advanced C++. And it is, I first ran into it when I first tried to do a chess game, an object-oriented chess game with C++, because I took the approach of saying, well, I don't want to have to write all of the special switch cases for every different piece on the board, because there's a lot of code that's the same when you play chess. It's like, okay, whose turn is it? Okay, which piece do you want to move? Okay, where do you want to move that piece? All of that data, that code should be able to be the same, but certain pieces cannot move the way other pieces move. So the way the move method gets implemented, that part is special and different depending on which piece, but all the rest of the code should be the same. And so, but when you try to implement this thing without learning the things that we're going to learn today, you run into a lot of walls, and it's very confusing, possibly why it's not working. And a lot of people just fall back to doing, this very, very bad, not bad, but very inefficient way of coding, which is, okay, big, giant case statements for every different kind of piece and duplicating all of this code. And if you ever have a bug and you got to come back and change that code, you got to change it for every different kind of piece, which is not what we want to do, right? So this is really what we're talking about today. So we'll use the monsters or creatures paradigm again today to describe that. So the idea again is we have this creature that has the ability to move generically. We don't know what kind of creature it is, but we've got a basic move. If you want to imagine it on a chessboard or a grid, you can. Maybe it moves up 1 and over 2, that kind of thing, right? But then we want to derive some monsters. Now, if this was a game, these monsters would have different, geometry. They'd have different health points, different kind of capabilities, and they would all have a unique way of moving, right? And maybe we have one that we just never got around to writing a move method for. We just ran out of time, so we'd like that one to fall back to use the base method. And in fact, we could have the game up and running, and they could all be moving generically, and we could have one developer whose job is to just work their way across 10 or 20 or 50 different creatures and gradually write some unique and interesting function that brings that character to life, that gets it to move in a non-generic way. So that stuff could happen while people are testing out the game. So that's a very, very cool thing. So that's the system we really want to have here, and that's what we're going to explore today, right? Unique implementations of move method based on the derived class. And we'll look at kind of a progression on how we get to being able to do that in a really, really efficient way, okay? So that's what we want to go for. So first thing we ask ourselves is, where are we going to store our creatures, right? Anybody think, okay, well, interesting. I have this mixed bag of creatures here, right? I've got Balrog, Warg, Org, etc. Where do I put them? Because I'm not allowed to create a vector of mixed things. There's no such thing as a vector of 8 different classes. So what do we do? Well, as it turns out, the way C++ works, we can make a vector of the base class, and that will allow us to actually store instances of derived instances of that base class. That's pretty cool, right? So now we can actually create or push back those instances, whether we kind of instance them before and push back a copy, or we do it right in line like that. Both ways are fine. And C++ will allow us to do that, which is pretty cool. So now we've got ourselves started here, right? Each of these things, if you remember, they carry with them their base class with the derived or base instance with the derived instance as well. These are instances of both of those classes that travel around like a little package. We only ever really think of the derived class or the child class, but they're all right there, right? So we could do this. We could say for auto ampersand, remember that's our reference, this creature. So that's saying, hey, create a reference variable. Don't take a copy of it, but create a reference to each of these instances, and then move that creature. So this might be somewhere in our game loop where we're drawing things every frame, and we want to update where the creature is, and then we'll draw everything, right? So we're going through all of our creatures that we've got in our game, and we're going to move them, and then we'll draw the screen, let's say, or draw our grid. So that should work, right? And you should remember that these are actual copies that are instances that are in that vector. And so we say this creature dot move, right? We're not saying arrow move, we're saying dot move because for this implementation, these are instances of creatures. Okay, has everybody got that okay? Any questions? All right, cool. So this is our kind of step one on our way to coolness, all right? So the compiler in this case is gonna statically bind that move method to each vector member. In other words, it's gonna say, oh, I see here that you have a goblin. I can tell that you have a goblin because you did a pushback of the goblin. And at compile time, I made a note and said, okay, you're pushing back a goblin, so I'm going to bind statically the move method for the goblin, unless you don't have one, and then I'll bind the move method for the int, right? Or for the creature or the base class creature. So that's called static binding, and that's not always good, right? Because we may not be able to get the kind of the fallback behavior we want. But we're gonna try that first and just convince ourselves that it's working. So what I want you to do is click into there. Oh, I'll give you the links. Bear with me here 1 second. I'll upload that file so everybody can get access to that. I believe I have it handy here. Sure, 25 links. And okay, I think that's there. Can you guys see that okay? Did it come through? Anybody? Give me a show of hands or verbal. I'm going to take that as a no. Nobody's seeing it yet? Can anybody confirm that they, okay, so somebody saw it. Got it. Okay, good. All right, thank you. All right, I was beginning to lose hope. All right, good. So we're on that first link there. So we want to actually go to this classes inheritance creature instance practice. So that's our #1 practice. So click into that one, and then go ahead and just do what we were just talking about. Fill the vector with 3 different instances of a derived creature. So these are creature instances. And then go ahead and iterate through a vector container, and you can use the range-based for loop that we saw there. And then check which move is getting called, right? As you go through that, right? When you call the move method, I think it's just going to print a little message that which move it is, and then look and see what it actually does, and see if it makes sense to you. So we'll give you just a minute or two. I imagine some of you jumped on that already. It should go pretty quick. But let me know if you have any questions. I'm just going to kind of set my timer here. Okay, and we're off. And I'm going to peek at the solution real quick just so I can kind of prefetch, as they say. I don't know if anybody of you have done hardware, but it's borrowed from the hardware industry. When you prefetch, you're grabbing something from memory ahead of time. So that's what I'm doing here. Okay. So right, yeah, everything's written for you. You just got to kind of develop the code in main there. Okay, another half a minute or so. So hopefully some of you are seeing that it is not actually doing what you might expect. Let's take a look. This is what we want to do. This is the right stuff here, right? So I'm just cleaning some stuff off my screen. we go ahead and we create some instances, right? Use the default constructors, and we'll throw a creature in there as well for the moment, right? So we can, at the moment, we can go ahead and create an instance of a creature, even though it's very generic. And then we can push back those things into, I guess I didn't push the creature back in this solution, but I can go ahead and push back the orc and the goblin and the warg. And then I can loop through and invoke that particular creature that I'm on and ask it to move. But as it turns out, even though you would think the compiler can tell what these are, it still calls the base class. And I probably misled you there on that previous slide. I meant it to be a bit of a mystery, but the static binding is actually going to bind to the base class, right? And so we don't get this cool effect that we actually want, right? Which is you know, and if we were to call O dot move by itself, we would get the move that's associated with the child class. But in this particular case, through this creature type, we're going to end up with the base move, which is not what we want, right? And we also cannot, this point here is maybe a little bit confusing, but you might think, okay, I'll just check and see what type this creature is, and then I'll do a switch statement that says what move to call based on the type. Maybe I'll do some casting of that type. So there's all sorts of things you might think you could do there, but that's not really the good path, right? So we're going to take you along the good path next to kind of take you in the direction that we want to do, because we really like it to be more intelligent than that. So so that has a lot to do with the way the base class has been created and the way we've defined that move method, right? We need to change a few things to allow us to have mixed kind of interpretive instances. We basically want to get away from static binding and go to what's called virtual binding. Now, I'll just point this out here because I've seen this come up in the past. People have asked, and it's an understandable question, is it okay to have vectors of creature references? And the answer is no. We can't do that with the vector class. It would be cool if we could, and it might seem to allow you to do some interesting things, but it's just FYI, if you think about trying something in that particular direction, it's not going to pan out very well. So we would like to not static bind. We want to have this runtime binding, right? And here's how we're going to get there, right? So first off, we're going to move toward pointers, right? That's an important part of this. We need to move towards storing pointers to instances of derived creatures, rather than actual storing the instances themselves. Oh, sorry, good question. I just noticed that. Yeah, it is smart enough. So the question is, why isn't the compiler smart enough? And it is, but syntactically, we just have to tell it that it's okay to do so. And without the word virtual, which we'll introduce here in a second, it just won't do it. And also, it won't do it with instances too. It has to be through pointers, or though I've not found any way that it's doable through instances. So we'll kind of explore this through the pointer and the virtual keyword approach, which generally is kind of the way most people go about this. So this is the big difference. So we have vector of creature pointers. Remember, this is our base class, right? And then when we push back, we're going to put those things on the heap, right? So we're pushing back a new goblin, a new balrog, etc., right? So those instances are on the heap, and we are pointing to them with an old school raw pointer there, right? From our vector of creature pointers, right? And even though a new goblin is clearly a pointer to a goblin, we're allowed to push it back into a vector of creature star pointers, similar to what we were doing with the instances in creature before, right? So we're doing that. That's okay because they're derived from creature, but now they are pointers. And now we could say for auto ampersand pointer, right? So we're saying don't make a copy of the pointer. This is just the efficient way to get that information. But then we say pointer arrow move, because this is an address of an instance, right? And we all know at this point that if we have an address, we use the arrow syntax to get at its members. So now we're moving definitely closer in the direction of what we want. We're hoping this is actually going to do something intelligent. So let's give that a try. That's we're going to find out. Still, it's not quite what we want, but let's let's go there anyway. We're hoping that it's going to call these things more intelligently, but what we're going to see here is it's still going to be statically bound. But at least we're doing it through pointers, which is the first key step. So let's try this. So this kind of iteration, hopefully will make this stuff stick. So jump onto that next one. So that one is called classes, inheritance, creature pointers practice, right? Because we're going to be storing creature pointers. So give that a quick look. I'll set the timer for us here. And I will peek ahead, see if I can give you some pointers. Not those kind of pointers, but advice. So very similar to the last one, just we got to use the new, right, to put those pointers in. And remember that pushback always makes a copy of things. That's a really important thing to note. But with pointers, it's okay to make a copy of pointer because it's just a reference into memory. So really just copying a 32 or 64-bit value into our vector when we push back. Now you can, like I said, you can have those things assigned to individual variables, which themselves would be, or like an orc pointer would be like OPTR, and then you could pass that into the pushback, or you could declare it right in line with the pushback. You could create your orc right in the parentheses for the pushback if you want to. Another half a minute or so. A little bit extra time on this one. Okay, there's our fun timer. Okay, let's talk about this one a little bit. And I think you guys will see where we're going here pretty quick. So, so we got our creature pointers, as which we're collecting those pointers in the vector. And we can go ahead and create our orcs on the heap, orc, goblin, warg on the heap, and then pass those pointers in. Or like I said, you could say new orc right in the parentheses there, totally fine. Now in homework 8, you're going to use make shared because we're going to be doing this with shared pointers, and we'll see a little bit of that toward the end of the lecture here today. But just to point that out, you know, here we're pushing back a copy of the pointer OPTR. We could have easily been constructing it right in line there, which is really what make shared does for us. And then we're iterating through creature pointers, right? And so we're saying creature pointer arrow move. So we're hoping that we're going to get the right move, and we're close, but we're still not there. There's just one more thing that we have to do to get it to call the right method. Right now, we're still just calling that generic move. So if you got that done, you would have just seen that, you know, basically you're just getting the creature move still, which is not going to get us to our chess game if that's what we were doing, right? So here's just the insights from there in case you want to come back and read this later. Okay, those are the key things. And also just a reminder that those creature references do not work there. Right? And there's the syntax for a shared creature, right? So we're doing it this way. We're going to look at doing it this way, right? If we want to move to shared pointers, right? But this is getting us close. So what is the thing? What is the thing that gets us across the line? Well, we need to introduce the word virtual as to indicate to the compiler that it's okay to defer any of that binding that usually happens statically at compile time, to defer it to runtime. It's not as efficient as a static binding for sure, because there are these lookup tables, these virtual lookup tables that the compiler has to keep around for the runtime environment. right? So there's memory and performance impacts of doing this. But it's what we want, right? It's going to save us writing code. We'll let the computer do the work. We don't want to have to write and debug extra code. So what we want to do is introduce this virtual method. So it's really just that, right? So if we put the word virtual in front of the type inside of our creature class, we let the compiler know, hey, this thing might actually be overridden, and we'd like you to defer any binding until runtime, and to choose the right move based on whether the child class has a move method or not, right? So if in the case of the ent, which was that creature all the way out to the right, it didn't have a move method, then at runtime, the runtime environment realized, hey, I'm going to have to use the creature move here. There's no actual move in the ent class, right? But for everybody else, it could choose the move that's in the descendant class, right? So in this case, we actually get the derived class if the move exists, right? And that's what we want. That lets us write some very, very clean code that deals generically with derived creatures, except where a method can fall back to something that's specific to that derived creature. And that is very, very cool. That helps you write some very, very efficient code. And that's really the pattern that we want to be followed, okay? So again, the key thing is just getting that virtual keyword in front of the method in the base class, to tell the compiler that we don't want to do static binding, okay? So here's just another way of looking at it. We have a pointer that refers to derived class, right? And an instance of the derived class that has the same identical method, okay? And we just need to tell the compiler to, that we want to call whatever is the most closest to the child method that's available, right? And indicate that it should depend on the runtime environment, and that's the virtual keyword. And it has to be done through a pointer. It has to be done through a pointer. So if we try to do it through an instance, like in our first practice there, it's just not going to work, right? Even if we had that the virtual keyword in there. It'd be cool if it would, but it's got to be done through a pointer, which is not something that is totally obvious. And this pattern happens a lot. And so I think it's really good to, if you're trying to problem solve these kinds of things and deal with things that generally are inherited like this problem comes up quite a bit, right? So just very good to know about this. So, so here's, let's see. So I think this is what we're going to do for our next exercise, is just go ahead and update our creature class and then do the same pattern again. And this time we should see, except for the ent, I think the ent still doesn't own its own move. So we should see these classes should move like the way those classes move, and the ent, I think, will move generically like the creature moves, right? And that's what we're after. Okay. Okay, so let's give that a try. So that is the classes inheritance creature virtual. Okay, so I'll give that a shot, and I'll go take a peek at the code again, just to see if there are any gotchas in there I can help you with. Let me start my timer. Now, to be clear, I'm looking at the comments in the code. We are putting pointers to instances in this container, not the instances themselves. I think the code comments might make that a little confusing, but we're really putting pointers to instances in the vector. Okay, another half a minute here. And other than the creature class, you shouldn't need to change anything else in the other classes. Okay. All right, let's take a look at that code. Hopefully I didn't rush anybody on this one. So here's our creature. It's super easy. We just pop the word virtual in front of that method. And that's just a hint to the compiler, again, not to do static binding. You don't have to ever even derive from this class. If you don't, then you've just kind of introduced some inefficiency into your code that you might not otherwise want to be there because it's setting up a virtual table and really doesn't need one. But if you are going to derive from that, that's the key piece that you need. That's really all you need on top of everything else that we did. So that's the cool thing. And so we're going to do one more here. We're going to see if we can extend this in the spirit of homework 8. We're going to extend this to go to shared pointers and see if we can convert all this stuff over. So I think I was trying to see if there's anything else. Oh, right. Yeah. So this key point here, this third bullet here is just pointing out that, yes, we could at this point, it's good to note that we could actually even still put a reference or an instance, pointer to an instance rather, of the creature, the base class into our vector, and all that would still work fine. It would still figure out which move to do. And, you know, that's assuming you want people to put the creature in, this generic creature in as one of the creatures. There may be cases, as we'll see, where we might want to restrict that. And we'll talk about that toward the end of the lecture for sure. So let's talk about the shared pointer thing, and it'll kind of help you dust off some of the surface of your brain for homework 8. So what we're putting in the vector now, rather than a creature pointer, we're going to put in a shared pointer. And remember that shared pointers have a template parameter as well, which is what are we sharing from? And that's going to be a creature pointer, not a creature star. All we got to do with a shared pointer is put in the type. So a lot of times it's hard to remember. You think, okay, it's a pointer, so I'll put in creature pointer. But no, it's not. It's just the name of the type. The shared pointer will automatically understand what you're doing there, right? So now we have these shared pointers pointing to instances of the derived classes, which we can do, right? So we can do this here. We can say v pushback make shared some orc, right? I think am I missing some parameters there? No, I think I'm okay. Yeah, orc doesn't have any parameters for its constructor, so make shared doesn't need any arguments. Okay, it's a little confusing when you have an orc that's a default constructor. If we had to give it a weight, we would put the orc's parameters inside of there for make shared, but in these cases, these are all just default constructors. So we're pushing into the shared pointer vector a instance of a shared pointer that points to an orc instance, right? So that's what's going on there. So we've actually created instances of orc, goblin, and warg there, and we're pointing to them, right? So that's our situation, and then we can loop through with that same code. I mean, it's the great thing about overloads, as we talked about before, is even though this is a pointer to this should be VSP, not V here. But even though this is a pointer it's a shared pointer, we have our overload, so we can say PTR arrow move, and it will get the move method from the instance on the heap that we're pointing to. So all that just works. You don't have to change that code, right? And it still get the dynamic behavior that we want, right? We get the right move, okay? So that's all a good thing. That's in the world of SharePoint. So let's try that. There are a lot of helpful kind of hints there for homework 8 again, regardless of which one you do. So this one's worthwhile doing. Take a look at the inheritance creature shared pointer link. I'll give you a couple minutes on that one. And notice or remember that if you find yourself using a new, then you're off on the wrong path, because make shared calls the new for us. So we really don't even need to do the new. About half a minute. Incidentally, I'm sort of guessing on these things for timing. So if you guys ever feel rushed, you can send me a private message if you want, and just let me know. I'm happy to adjust. I'm just trying to make sure that you don't leave anybody behind here. So if it's too much, too little, feel free. Okay, so let's look at that one. It's pretty straightforward conversion, but good to practice it. So here we've got our shared pointer of creature inside of our vector, right? So VSP there. And then we can create a shared pointer instance myOrc here, which is an instance of the shared pointer class. And then we can pass that in via the pushback. And remember that pushback is going to make a copy of that myOrc instance. But since that is just a shared pointer, that's okay, right? We're just making a copy of a shared pointer. Shared pointers have a copy constructor, totally fine. So it just gives us another way of accessing the orc instance on the heap, right? But we could also do it this way. We could put the make shared right inside the pushback. And so it just constructs a temporary copy of that shared pointer of the goblin in this case. And that gets pushed back as a copy onto the VSP vector. Same thing there with the warg. And then we can iterate through and same code, right? We can just say creature pointer move. And because our creature class presumably is still virtually, has a virtual method in there, virtual move, then it should call the right one, right? And we are still, at the end of the day, working through a raw pointer, even though it's somewhat abstracted by this shared pointer that we're working with here, creature pointer. But the way we do it in code is the same. And so we can just think of it like a pointer, and it all works out, which is very cool. So we've kind of combined this concept of RAII, or resource allocation is initialization, horrible acronym, but very common. We're combined that with this virtual method move and the use of pointers to be able to make some pretty cool code, actually, to do things like chess games, to do derived creatures, all that stuff. And really, that is the best way to go about doing it. Right? If you're going to do it in C++, that is really going to be the most modern and optimal way to kind of collect those. And again, the reason we do that is because we don't want to write big switch statements that test to see, oh, well, what kind of derived instance is this? We want to actually know, oh, it's a creature instance. And so there are certain things that we can treat as being common, okay? So this kind of sums up those points. I'll just see if there's anything I've missed here as I kind of go through them. Yeah, right. We don't really necessarily want to care what kind of type it is. If they all have the same methods, what we call the same interface, the method interface, which we'll talk about in a minute, then we can treat them as kind of the same thing when we process them in loops. But if those methods are intelligently falling back or using the most derived class first, then we get appropriate behavior based on how we implemented that. Okay, so it's a really powerful way to do it, and without it, it just gets really kind of messy. right? And so we need to do that through pointers as well. And we need that virtual keyword, which is important, which sets up that virtual table, which is pretty much hidden. But if you want to dig into it, you can do a little research on virtual tables. You'll find it out there, definitely. Okay. Okay, any questions? I know I've kind of gone through a lot of that stuff. Hopefully it was progressive and not too overwhelming, but anybody have any questions on the application area or kind of what the key takeaways are there? Okay. Well, you won't see this in homework 8, but I guarantee you'll see it in homework 9. I'm still kind of mulling over how much to throw in 9, considering what we've covered this year. But definitely this concept is very important. And so I'll very likely be having some form of it in there. So please take the time to learn it and understand it, mostly through these exercises. And then when we get to homework 9, you'll have lots of supporting material to help you kind of solidify your understanding of it. Okay. Question. Yes, good question, Jackson. Yeah, you know, how much how much overhead? I don't know. I've never measured it. I think the virtual tables have been around for a little while. I think they might have some other applications as well. But I think that in order to achieve this behavior, there was just no other way. I imagine that most languages, again, like Java, that are more runtime, have this kind of thing always, and that you basically can't not have it. And so, you know, if you're not doing this kind of thing, you can get some very, very efficient code. That's the benefit of C++. But as to, yeah, as to how we do it, how much it costs, it would be interesting to run a test. You know, you'd have to do, you couldn't really compare. I mean, wouldn't be a fair comparison against Java because it has other runtime costs. But yeah, it'd be interesting to see just as a raw test. I have to think of a way to do that maybe, and we can do a timing on it. And it has a memory impact as well, although I don't know that it's how it scales. It may scale depending on how many instances you actually create, but I have to check and see. Good question. Okay, so the last 2 things or 3 things, I think we got time for these. Yeah, not too many more exercises. I think maybe that's it. Maybe we got 1 or 2 more. So there are a couple. There are a couple references in C++ that are inherently confusing, because when you hear somebody talk about something like an abstract class or an interface class, you think, there must be a keyword somewhere called abstract, or a keyword called interface that makes the class an abstract class or an interface class, because these are 2 ways people talk about classes. Well, the truth is, no, there is not, right? And so these are important concepts, and they do exist in other languages, but the way we create them in C is a little bit clunky, to be honest with you. So we're going to look at and talk about these 2 things briefly: an abstract base class and an interface class, why we have them, and how you go about creating them, just briefly. So, so an abstract base class is kind of a blueprint, right? It's used as a base class only, and it's generally not instanceable. Well, it's not instanceable by definition, right? And the idea is that, you know, we don't really, if you're the senior developer, you kind of want to set the design structure for everybody else. Maybe you're making a giant game or a 3D modeling tool or a, you know, DNA analysis tool or something, and you need a base class, right? And so you're the one in charge of doing that. So you don't want to really be too imposing. You want the derived classes from your base class to be able to implement things maybe their own way. But you don't ever want to run the risk of anyone instancing your class by itself. It should always be instanced through somebody else's derived class. That's an abstract class, right? So how do we prevent a class from being instanced? Because it's basically not going to be complete. And the way we do that is we need to actually forcibly remove any default implementation of a particular method, right? If that method doesn't have an implementation in the base class, then it can never be instanced, right? The compiler won't instance it. And the way that we do that is with this very interesting syntax here. We say virtual void and whatever the name of the method is, and we set it equal to 0, right? So just that one method, doing that to any one or more methods in a base class will always prevent that particular base class from being instanced by itself, right? That defines an abstract class in C++. You wouldn't think it to add that equals 0 is it, to one little method in a giant class is what does it, but that's the trick right there. So if we don't want anybody to ever instance our base class, we just have to have what we call a pure virtual function. That's what that is. There's virtual, which we learned about and we looked at, but now it's called pure virtual. Pure virtual is the equals 0 part. It removes the implementation in the base class for the move and prevents the compiler from ever instantiating that class. And so if you try to instantiate a class like that, it would scream at you and say, hey, this is an abstract class. It's got at least one pure virtual method. Can't do that, right? And so there's this weird connection between, well, you know, if I have a pure virtual function, why don't I, you know, why do we call it an abstract class? You know, it's just a different way of describing it. It's very abstract. It can't be used for anything else, right? But it's basically and only caused by this syntax right here, basically removing the implementation for the move method. Okay, and you might think, well, why is it like that? Well, I don't know for sure, but I imagine that because, you know, it could be prototype, it could be implemented out of class in some other file somewhere. But when we set this syntax here, inside of the base class, it says, don't even look for out of class implementations of this somewhere else. It is not going to happen, right? So that's just one way of definitively shutting that thing off, right? And you've seen a syntax similar to this where we tried to delete copy operators, right? We said equals deleted kind of thing, which is a C11, C++11 version change. So, but this is the way we actually turn something into an abstract class, okay? So here's what it looks like on the left, on the right, okay? So you can see this one's pure virtual over here, and this one's not. So this one can never be instanced, and this one can. And we can actually have an implementation here directly inside of the creature class, or it could have been implemented out of class, okay? So that's pure virtual and gives us what's considered to be an abstract class, okay? So it's good to know that, okay? So I think we're going to do that. And I think just all you're going to see here is that the creature, you know, the instantiation of the creature in main cannot happen once you turn this thing into a abstract class by using a pure virtual function. So give that a try. Should be pretty quick. And then we'll move on to interfaces and then to multiple inheritance. Okay, maybe another half a minute. Okay, so for those of you that tried that, you probably, if you ran it before, you kind of, before and after, you'd see the compiler error after, if you didn't comment out the attempt to push back the new creature. Basically, the compiler is going to tell you that it's an abstract class and you cannot actually instantiate it. So no surprises there. Just change something back here real quick. And right, back at it. Okay, yeah, so let's take a look at that. So yeah, we just added that equals 0 in there, and then that basically undermines any instantiation of that creature inside of main. Okay. And again, it's really, if it's a blueprint, you just don't want it to be used by anybody. That's really all that's about. Right? And there's what we did inside of main, right? We just commented out that pushback of the new creature because it won't let you do that. It'll complain. Okay, any questions on that? Oh, I see one. Class can still be instanced when it's called by the child. The base class? Yes. I mean, it will be part of the, I mean, yes, it will be part of the child class, and therefore it's still accessible through the child class. I think if that's your question, but standalone, no, right? Actually, that's a good question. Yeah, it's there. I'm pretty sure. That's a good question, though. Let me check and see. I think we might have a slide on that, but I may have to go back and double check on that one. Here's just some insights, right? Virtual function that's not pure, right, can have an implementation, right? We talked about that, yeah. So that was kind of our earlier thing. So I'll come back. That's a good question, Jackson. I will check on that and find out, like whether we can basically use those scoping access syntax to get at the base class via an instance. I think maybe not, which makes me wonder how much of the base class is actually included in that instance. It's a little unclear to me. So an interface class. So an abstract class, interface class is yet an even further devolved version of our base class. We're going to take away even more things and just focus on the interface, right? So this is kind of like when someone says, hey, look, I don't know what memories you need in your class, in your derived class. All I know is you're going to have to support the following 5 methods, and they have to have the following function signatures. But you can implement your class any way you want as long as you follow these rules. And so an interface class is kind of, this happens often when third-party development tools are being made. It's like, look, here's how we all have to agree that all interfaces have to be the same for these kinds of objects. So, you know, some designer is going to establish the base interface classes, and then everybody gets to go ahead and implement their own versions of that. So there might be, an example could be OpenGL or a 3D graphics library where we say, hey, we've agreed that, you know, all you people can compete out there to have the fastest library on the planet for drawing 3D primitives in games. But so that we don't drive the game developers insane by having them learn a different version of OpenGL every time, we're going to maybe have these classes that will specify the interfaces that everyone has to follow. And these classes are actually the traffic cops that ensure that, you know, if you have to derive from that interface class as the base class, and then you can go on about your business. And sure, if you want to have extra variables in your special version of it, that's great. In your derived class, if you want to have some extra member variables, you can. But that's the whole purpose of an interface class, is allowing us to just kind of put out a blueprint and not being overly specific about it. So an abstract class has this pure virtual function we talked about. An interface class is exactly that, but with only those pure virtual functions, no data members, no constructor, right? That you don't see too often, but it kind of matches that example that I was talking about. So there's our pure virtual method. It's an abstract class, right? And so here is our interface class. No constructor, right? That's a big difference, right? And so that might be a hint to the previous question that Jackson was asking. So without the constructor, certainly you wouldn't be able to instantiate it. But here I think maybe the constructor serves the purpose of allowing us to bundle it into the instance of the child class, so we can at least invoke the constructor through the child class. But again, I'll check and see if I can't get to a more clear answer on that. Right, so that's our interface class versus an abstract class, right? Okay. Questions on that stuff? Okay, cool. All right, hang in there. We got a couple more things. This next one, I don't think we're going to have any questions on any tests on this, but I just want you to know about it in case. I think somebody asked this a couple lectures ago, but we've seen the using keyword before. We're going to see it used in a new way here. I just want to introduce it to you. We don't have any exercises on it. But very often we want to take one of these larger classes and narrow it down a little bit by hiding some members and maybe renaming some members to make it seem like it's doing something a little more logical for our derived class. It can remove a lot of complexity, because if you're reading the documentation on a very simplified derived class that's hiding a bunch of stuff, then maybe it's easier to use, and maybe you don't use it in an inefficient way. So there are a lot of reasons why you might want to do that. And so we had some experience with that in the stack and queue and the prioritized queue containers. You remember these were called, what did we call these? Now I'm blanking all of a sudden. I did it to myself. But basically, these are adapted from those other base containers. And through the hiding of these methods, we make them seem like they're a custom container, but they're really just a special derived class that has a number of methods hidden, right? And maybe it has some extra members thrown in as well, right? So that's why we would actually do that hiding or exposing. So here's how we would do that. So if we have a base class foo that's protecting X, that means we're going to keep it in the family, right? Foo Junior can have it, but it can't be accessed publicly through an instance of Foo Junior. But Foo Junior can introduce this using inside of its public region. So it's not just the actual reference of using, but we actually have to put it in the public region. So by calling that out here, notice we're not doing anything with it. We're just sort of registering. We're saying, hey, that foo X is now, by order of Foo Junior, has been moved into the public area. And now we have exposed X in a public way, even though it was protected from foo. So the derived class here is actually kind of overriding the protection status that the base class actually established. Yeah, okay, that's right. So that's using. And remember, we're using our scope syntax here to actually specify which X we're talking about, to be super clear, okay? So now we can say foo junior FJR, and then we can actually access X, right? But we can't go ahead and access it through the base class. We can't say foo :X, because that's still considered to be a protected access. But by re-registering it down here, we can get at it through Foo Junior. So we change its classification status through Foo Junior only. Okay. Now I think the opposite is also possible, right? So we can, in the private area down here, apologies for my very compacted syntax, but this would be our private keyword that we know, we're very familiar with. I've just moved it to the bottom. And I have using foo get X. So I'm basically saying, hey, what was public up here, get X, I am now re-registering as private in the context of any foo instance, right? So I've moved it to the private area. So I could, conversely to our previous slide, I could say, oh, okay, well, I know that getX is public in the foo base class. So I can say foo junior or FJR dot foo :getX. That's okay. But since it's been moved to the private area in foo junior, the FJR get directly would not be available, right? So I'm not sure why you would want to do that, but that's how you would actually change that designation status, right? It's all about where you put it relative to the public or private status here, okay? And I could change something to protect it if I wanted to by putting the protected keyword out there and then put the using thing there as well. Any questions on that? Okay. Hang in there, we're getting there. I know this stuff's a little bit dry and a little abstract. These last two are just like FYI, because sooner or later you'll see that syntax, you'll think, what is going on there, right? We're just re-registering their protected status, okay? Nothing too magical about that. Okay, so last topic for the day then is multiple inheritance. And I certainly owed you a practice on this, but there's just no way we're going to get this done. It's interesting stuff. I think there will be a question on this on our upcoming quiz, but I'll give you some heads up about that if there is. It's important to know because there are definitely some good reasons for using multiple inheritance, but it can be a little tricky. And here's the idea. So I'll take my foo and goo classes here. So think of them as two parents, and I would like to derive a descendant from those that inherits from both of them publicly, right? So I want both of their methods. I want method F1 and F member, and then the G1 and G. And so that's what I'd like to do. And I'd like to create a composite for that. And there are surprisingly a lot of reasons you would want to do that in code, right? And you could imagine, it's like you could have somebody working on the goo class. There may be a specialty designer in a particular kind of class, and that's their responsibility. And somebody else, so we're dividing and conquering two non-overlapping aspects of a derived class that we want to work in, right? And this could be a great way to allow both developers to work simultaneously, maybe 3 developers, right? So here's how we do that. So we declare, you can call it whatever you want. I've called it foo-goo, but we derive from foo publicly and goo publicly. And this order is important. This order of important that we listed here in this particular case, remember, we're not in the initializer list here. Order doesn't matter here. But up here, this order means that we're going to derive first from foo and then from goo, right? So that's the construction order that we're going to see, right? And if I flip that around, it might not make a difference, but in a lot of cases it does. So good to be aware of that, right? So let's take a look at maybe a real world example. So you're a grad student, you're still a student, but you're also teaching some classes, right? So you're going to have some members and some methods that are specific to both classes. Now we could try to create 3 classes, a student, a teacher, and a grad student class. But as you can imagine, the grad student class can end up copying a lot of code that exists in the student class. Nobody wants to have to go copy and debug and update 3 versions or 2 versions of the same thing in 2 different places, right? So what we want to do is be able to inherit from both of them, right? And that way you can be graded as a teacher, graded as a student. You can have methods that are specific to each of these functions. It all gets kind of combined together, right? So that's just one example. So here's how we would instantiate that. And when we do that, we're going to get this bundling of the base class, both base classes instanced on top of the derived class instance, right? So it's all there in that one instance. And as you can imagine, if something was static, then it's going to be back in the class, not in the instance. But for everything else that's not static, which is mostly how we've written stuff this semester, it's going to be bound into this little package that goes with the grad instance GS, okay? So that's the whole instance of grad. And it allows us to leverage those ancestor class methods like we would normally, right? When we have just one ancestor, okay? So that's a pretty common thing. I put a link there for you just to explore. We're not going to do an exercise on it, but it's definitely a good one to know. And if you do have it on a quiz, I'll probably come back and lecture and give you a refresher, maybe an exercise or some hints on that, just so you so it sticks in your head a little bit. Now there's one, wait, before I go on, let me just see if anybody's got any questions on that. Okay. Wait, let me see if make sure I haven't missed anything. Okay, good. All right. All right, so bear with me. I think we're going to land on time here, around 7:15. So that's our multiple inheritance example for the grad student, right? So now there are situations that can happen that can be quite confusing if you don't know your way out of the box, so to speak. So if you did something like this, you thought, oh, I love inheritance. I am going to create a person class that's the base of the student, and then the student can pass on things to the grad, and same way with the teacher, right? Because the teacher is a person too. So you might have a name and a zip code and phone number and all that good stuff, right? But this can present a problem, because if you create a grad instance, we get this kind of package here, right? By default, we get 2 person instances that get packaged in there. You would think you'd only get 1, but because of the way this code ends up looking and executing, you end up with 2 by default, right? So that's the whole thing. And the problem is that a member from the base class name is ambiguous. When I say gs.name up here, well, which name am I referring to, right? Am I going through student, or am I going through the teacher's name, right? They each have their own copy, which is just not what we want at all, right? Because if I change one of them and then I don't change the other one, you know, it could cause all sorts of problems, right? So we really need to tell the compiler that we know what we're doing. We don't want that situation to happen, right? And so there is a form of derivation called virtual derivation. It's unfortunately, it's another different kind of use of that virtual term, right? So here, if I say I still want to create a grad and I want this kind of result, what's the code that's going to allow me to create that? Right? I have to put some information into the way these things are derived so we can avoid that, right? So if we can inherit virtually from these things, then we can do that. And here's how that looks in the code. And sorry, this is not laid out hierarchically. I just kind of ran out of room on this page. But there's our most base class person there, right? And the student is going to derive public virtual from person, right? So I think this is probably similar to that late binding dynamic kind of situation where we're letting the compiler know that there are more things coming here, and you shouldn't statically bind things until everything's compiled, right? And then here's our virtual teacher derives virtually from person. So if we do that at this level, right? Not at the child level, but actually at this level. And then we actually build our typical kind of multi inheritance here from 2 different classes. Things will work out just fine. At runtime, it will figure out that we only really need 1 of these person instances in our little package of instances, right? So that's how we get around what's classically referred to as the diamond problem when we're designing this way, okay? And that's getting a little tricky. You start doing that kind of stuff, you know, you're definitely playing around with some pretty potent stuff. It's cool, but it definitely can trip you up, right? So that's kind of the takeaway on that stuff. So the child essentially can call the grandparent's constructor directly via its initializer list, right, if it wants to, unless the grandparent or the most base class has a default constructor. Okay, so there's a couple links there to let you kind of look at that code, but we're not gonna do any kind of big exercise on that. It won't be in any of the homeworks, but it is definitely a good one to learn and be familiar with. Any questions on that stuff? Okay, cool. All right, you guys are being very agreeable today. All right, so just look ahead for next time. We're going to look at threads next time. And so part of dealing with threads, we'll see that the Chrono library is very useful for that. So we're going to do a little bit of introduction on the Chrono library, which will be pretty brief. And then we'll look at threads, which is really a very different way of coding. And I'm glad that we have the time to introduce it to you, because often it's just not introduced in a class like this. But we're essentially going to learn how to run kind of 2 or more programs at the same time, where those programs essentially have shared memory. Now, I should have put the 2 or more in quotes there, because we're really running the same code, but maybe calling different functions from that same code in parallel, right? Or 4 at a time, or 8 at a time, or 100 at a time. Depends on the kind of processor you have. But imagine a bunch of little particles flying around in a 3D simulation where each of those particles can be running a different part of the code at the same time as some other particle, right? You have maybe 1,000 threads running. That's a little bit extreme, but that's kind of the idea. It's like you write the code once, but you want different things to be able to exist at different times in your code, and yet still potentially have access to the same vectors or memory storage. So we're going to learn all about that stuff. That's going to be about 2 days worth of lectures. And part of that that we'll learn about are worker functions and this thing called mutex, or lock guards for protecting data. Because what happens quite often with threads is they fight, kind of like siblings. They'll fight over the same piece of data in memory, and they'll keep changing. One will change it one way and one will change it back. And as the debugger, you can never figure out what's going on. So the mutex is one of the tools that we'll learn about that will allow us to protect the data at a certain time and allow it to be owned by somebody for a short period of time. But that's what we'll talk about on Tuesday and Thursday of next week. And if we can, we'll try to incorporate that into our last homework. I'm trying to put a few new things in there for you so it's not too much, but we have a little bit of time before we get there. Any questions today? I know a couple of you indicated interest in staying around. That's great. I will definitely be here. But any questions on the assignment today or homework or anything? All righty. Well, thank you, everybody. I will talk to you on Thursday then. Have a safe week. And I will talk to you then. And I'll be here. I'll stay online. Okay, thanks.